Hello everyone, my name is Vinicius and I'm here today to present the SIS project from Capital Rocket Team. First of all, we're going to talk about our mission performance. We did some altitude predictions which gave us an apogee of 1.1 kilometers, and the impact dispersion analysis that we did gave us a ellipse of main axis radius of 500 meters. We can also see the component weights. All the major components are presented here, and we had a total of 26.5 kilograms in mass in our rocket. And here you can see the model thrust curve. This data was obtained during the blowdown analysis, and this was the curve we use in all of our aerodynamic simulations. Here is presented the stability margin graph. As you can see, our rocket maintains stable during its main flight, which is ideal, and you can also see the center of pressure and center of gravity plots here, and the angle of attack.
Hello everyone, my name is Paola. I am the project manager of Capital Rocket Team. I'm going to talk about the Propulsion Subsystem. The Propulsion Subsystem of the CDC project is made of an oxidizer tank and a combustion chamber. In the oxidizer tank, we have the vent system, which is for the pressure relief of the tank. And we have a lot of connections from the tank to the combustion chamber. In the connections, we have also three main valves, which is the ball valve, the check valve, and the quick coupler. In the combustion chamber, we have the injector system, which is composed by injector plate and a manifold. We have the pre-chamber, the fuel grain, the post-chamber, the nozzle, the coupler, and a thermal insulation, which is an EPDM rubber. To analyze the propulsion subsystem, we had a lot of simulations first. We have done the structural simulations, the blowdown analysis, a thermal insulation, and internal ballistic simulation. We also have done successfully the cold flow test, the hydro test. We're going to do in the next week the fire test. The Avionics subsystem is made of two parts, one inside of the rocket, another one outside of the rocket. Inside of the rocket, we have also two parts, one upper in the nose cone and another in the middle of the rocket. In the nose cone, we have a telemetry system, a GPS, and IMPO system. We have also antennas for communication and a lot of batteries. The second part of the avionics subsystem is the middle of the rocket, which is composed by the recovery system, electronic, an strotologger, which is an altimeter, BMP, and Arduino. We also have the vent control system, and the thermostat for the valve heating system. Outside of the rocket, we have the filling procedure system, which is made of a load cell for measuring the mass of the rocket. We have the ignition system, and also the decoupling of the whole system. We have also communication made by LoRa.
And now let's talk about the recovery subsystem. We're going to use two different parachutes. The drogue parachute is going to open at apogee, and it has 0.7 meters in diameter. And our main parachute is going to open at 400 meters in altitude, and it has a diameter of 2.3 meters. Both of them have a spill hole of 20% of its diameter. The ejection system is very simple, and it uses a CO2 cartridge to eject the nose cone at the right time. And we also use a tender descender to hold the main parachute in its place until it's time to release. And finally, the structure components. Our rocket is made out of fiberglass and aluminum spars, and all of the components that we talk about in this video are presented here in its final position in the rocket. We can also talk about the nose cone, which has a von Karman shape, and our fins, which has a airfoil in the shape of a pointed D-tip. Our rocket has 2.1 meters and 15 centimeters in diameter. And here are the costs and the schedule for our project. Thank you very much, and we are very excited to go to the competition.